simulating the PV cell. In this session, let us see how we would go about simulating a PV cell. Before we go into the nitty-gritty of simulating the PV cell with ngspice, let us see what we want to actually do. We know that the PV cell has a model like this. Now this model has to be simulated, and what is it that we want to see? We would like to see the IV characteristic at the terminals, the voltage across the terminal and the current flowing through the terminal and the external load. And how is the IV characteristic? We know that it is something like this. If we have I on the y-axis and the voltage on the x-axis, the IV characteristic looks something like this. So how can we achieve this IV characteristic? By simulating this model in ngspice. Consider we have an external load R0 like this. Now if we just have this external load R0 like this, there will be a current flowing through this and a voltage will develop across R0. A DC voltage will be there and you will have a DC current. It will give just one operating point on this IV curve. We need to have many operating points. So therefore, we make the load resistance R0 variable. In such a case, by making R0 0, you would achieve V0 of 0. There will be a short circuit current flowing through the R0. And when you try to increase R0 to a larger value, this I into this R0 value at that point in time would give you a voltage which would sweep the x-axis. So basically we would have an x-axis sweep voltage value, and when you measure the current, you would get the various points which would represent the IV curve. Alternately, what you could also do is replace this resistance with a source. Incorporating a voltage source like this across the terminals will also provide us with this IV characteristic. However, the voltage source should have a time evolution in this manner. Let us say we have a sawtooth like this. In this manner, this would provide the sweep for the x-axis of the IV characteristic, this voltage sweep, and the current will accordingly vary and provide us with the points for the IV characteristic. What can be noted is that this wave shape for the voltage of this voltage source need not be sawtooth. It could be triangle, or it could also be sinusoidal, as long as it is a varying function of time, so that this x-axis sweep is provided. So normally we will use a sinusoidal voltage source here, because that is easy to make and easy to implement. And even in the simulation, we can try putting a sinusoidal voltage source here and see the performance of this model and obtain the IV characteristic curve. After we have obtained the IV characteristic curve, we will try to vary RS and see what is the effect on the characteristic. We will try to vary R shunt and see the effect on the characteristic, and also try to vary the temperature, operating temperature. let's say 10 degrees, 25 degrees, 50 degrees, and see what is the effect of temperature on the characteristic. So all this, let us see how we go about doing in simulation using the open source ngspice software. Let us now go through the steps in simulating a model of a PV cell in ngspice. For that, first let us create a new folder, and let me call it as PVSim, and this folder PVSim will act as our simulation project folder. It is right now empty, and into this all the files related to simulating the model of a PV cell will be placed. Let us go to the applications and pick up the GEDA schematic editor. Click on that. You will get the schematic editor GSCHEM. This is where the circuit schematic will be drawn. Maximize that, and you have the empty blank schematic page. Before you begin drawing the schematic, let us save this file and give it a meaningful name. So go to save, and then into the PVSim folder that we just created, we will call it as pv.sch, and then we now have a blank pv.sch file. Now into this page, let us drop in the components and then connect them to form the model of a PV cell. Go to the add component box, and here you select, there are many libraries with components. Now let us choose the ones relevant for this particular project. I am choosing Spice Simulation Elements, and in that I am selecting the Spice Include directive. You place that here. I will explain about that a bit later. Then we will choose the Power Rails library, and that we need two important symbols. One is the ground symbol, without which the simulation will not proceed, and then the generic power symbol. It is a label. We need to label the nets, so let us place that here. I will explain that later again. Next, we choose the basic devices library and open it up, and then we need to choose few components from here. One of the components we need is the current symbol for the photocurrent. Then we need to choose resistors, because the PV model has resistors in its circuit model. Resistors, there are two symbols. I would prefer the box type symbol, so let me place two resistors there, one for the series and another for the shunt. Then we need to pick a voltage source, so let me pick this voltage source and place it here. This is for connecting across the output terminals to see the IV characteristics. Then we need to pick a diode, because diode is again another component that is an important part of the PV cell model. We pick the diode, and we have here almost all the components in place. We can close this. Now we need to combine this into a circuit. Pick the current source, rotate them like this. Pick the voltage source, rotate it accordingly. Pick the diode, rotate that. Take the R shunt, which will become R shunt, rotate it accordingly, and then place the series component, and then next we need to wire them up. Before wiring, you could also name the component parts. So let's say this is IP, indicating the photocurrent. You could have D1, this is the diode part of the model. Then the R shunt, I can say RSH, the series non-ideality or S, and the voltage source to be connected to the output, we can call it as V0. And the output node label, we can call it as NV0, node of V0, NV0, like this. Now let us go about connecting the components with the wires like this as shown. After having connected the wires appropriately, the circuit looks like this. And here for the include directive also you can give a designator A1, and then for the file you give it right now as pv.sub, and into this pv.sub we will put all the models related to the circuit. I will describe that a bit later. For now, just leave it as pv.sub. Next, I have given values to the various components. Let me bring it to a close-up like this. So for the photocurrent part, I have given a 1 amp as a value. You just have to enter into the value attribute, and for the resistance also into the value attribute I have put 1 mega ohms, and the series resistance 0.1 ohms. And for the V0 source I have given as a sine source. We need a monotonically varying source here at the output terminals so that we have x-axis sweep for the IV characteristics. I have given a sine source from 0 to 0.85 peak, 50 Hertz, and all other parameters 0. So you can experiment with that, and I am calling this node as NV0 as I said earlier. Now for the diode, I have given the value as DEF, which means it is a model value, and that model will be included in this pv.sum. Okay. So this now completes the entire schematic. Now we see that in the pvsim folder, the schematic file pv.sch has been created. You can always double click on that and then see the circuit and edit it at any time that you like. Now you should note that ngspice doesn't directly use the .sch file for simulation. It has to go through one more step of conversion to a netlist, and ngspice can only recognize and use netlist for simulation. So now what we will do is to create a netlist. Before creating the netlist, there are two files that need to exist in this folder. One is the pv.sub. Recall that we had mentioned pv.sub here in the spice include directive. We need to provide that file even if it is a blank file. And the other one is pv.cir, the circuit file, in which will contain all the analysis that ngspice is supposed to do. So to create these two files, let us go to a text editor, and just a blank file we will save it into pv.pvsim as pv.sub. Now this will save and you will get one blank text file pv.sub. We will also create one more file and name that as pv.cir, which will contain all the analysis that ngspice is supposed to do. Now you have the three files pv.cir, pv.sch and pv.sub. Now using the sch and sub files, we can now compile and create a .net, pv.net. Now let us see how we go about generating this netlist file. For this, let us go to a terminal, open a terminal window, go to the simulation subfolder and check that we are in the right folder, the right files. Now here let us type in the command for generating the netlist. gnetlist -g spice-sdb output to pv.net input.sch. So this is the command for generating the netlist, and it would have generated the netlist here. So see that here a new file has been created in that folder, the fourth file, which is pv.net. So if you read through the pv.net netlist file, open it, the initial statements are automatically put in by the gnetlist program. See here the first file, include pv.sub. This is coming from the spice include directive, and this are the netlist of the circuit that we put in into the circuit PV model circuit diagram. I'm going to draw your focus to this point. D1, the value that we gave was DEF. It is the name of a model. Right now it doesn't have a definition because pv.sub is blank. So we need to define this DEF model within pv.sub. Then the netlist becomes complete. So let us do that and then recompile and generate the netlist. I'll close this and open pv.sub. So that is open. The first line is normally a comment line, but you put in some comments. So let me type in something, library of component models, something meaningful. Then it is better that you have some demarcation. Star would indicate comments. So let's say class of diodes, again star, all these are comment lines. Now starts the model dot model, the name of the model which we gave DEF, a diode model within these parentheses, and then I'll just close it, indicating. Now all others are comment line. All the lines starting with a star are comment lines. The dot model DEF, D within parentheses, is the model default diode model that we have put. If we want to have any special diodes, we may have to fill in the parameters within this parenthesis. That you can look into the datasheet manual of SPICE and then appropriately edit the models. Now for now we will put this default model and save. That is saved. We close this and then redo the generation of the netlist. So when we redo the generation of the netlist, the new netlist would have been created in pv.net. It would have been updated. Just see that with respect to the previous one, it has been updated. There is a model DEF which has been now included. It is residing in pv.sub. So the diode DEF is now defined here, and then all the portions of the netlist is fine and okay, and it is supposed to execute well in the simulation. So now we have a full-fledged proper netlist. We need to put in the analysis within the .cir file. So let us see what we will write in this .cir file. Now open pv.cir. It's a blank file. First line is again a comment line. I'll just type in simulation of PV cell. I will leave one more line and then put in the analysis. I will put a .tran transient analysis with print step of 0.01 milliseconds, 5 milliseconds as the end time, and UIC, use initial conditions. I'll also include .include pv.net. That is, we include the pv.net into this. Okay, this 5 milliseconds is coming from the schematic. Where if we go to the schematic, you see that we have an output which is a sinusoidal source 0 to 0.85 peak. This is 50 Hertz, which means 20 milliseconds period. So in a quarter of this period, it would have reached 0 to 0.85 in 90 degrees time. So it would have reached the full sweep value of the x-axis. So that is why I have given 5 milliseconds here. That should be sufficient. Save this, and that's it. We have all the files here. ngspice will use this and these two files. That is it. We will be using this. This will in turn call pv.net, which will in turn call pv.sub. Now opening the schematic file and zooming in the circuit. Now let us say we would like to see the set of IV characteristic curves with RS as a parameter, as RS varies. So let us see how we go about simulating this IV characteristic curve with different values of RS. So now open the terminal window, go into ngspice pv.cir. So now you are in the ngspice environment. You can use listing and see what is the netlist as we that has been loaded. Now what we want to do is we want to change the parameter of the RS, the series resistance. So we could say 0.1, 0.3, 0.6 ohms, just for example right now. So how do we go about doing it is we will execute this run of the simulation with RS is equal to 0.1. So you just type in run. So one set of simulation is executed. These are the node voltage and the branch currents that you see. If you want to see the vector names, just put in display. So when you type in display, you see these are the vectors available to you. The voltage of node 1, the voltage of the labeled node, the time, and the current through the branch V0. All these vectors are grouped into one called tran1 group. When you type in set plot, you will see that tran1, which is the current plot group, okay, is named tran1. It is the simulation of the transient analysis. So now if you alter the RS value to 0.3 ohms, let us say. Now the RS value is altered, and now you run the simulation. Now I get another set of vectors here. Type in set plot just to show to you that now you have a tran2 simulation. This is the second simulation. So I still have the vectors of tran1. I now have the vectors of tran2. Now let us say that I also alter once again RS to 0.6 ohms and run the plot, and I will type in set plot. You will see I have tran3, all the vectors corresponding to tran3. So each of these plot groups will have the vectors of all these node current voltages and currents. Now let me shift the current plot to tran1, that is the first plot at RS is equal to 0.1. you can check that. Again, type set plot, you will see that the current plot now is tran1. Now I will plot. Before plotting, let me set the background color to white, set the foreground color to black, and now plot. Now what are the things that I have to plot? I have to plot the IV characteristics. The x-axis, I will take it always corresponding to the transient analysis 1, and the y-axis is the one which will vary for the other for all the other transient analysis at RS is equal to 0.3 and 0.6. So plot current V0 versus NV0, the voltage across the output terminal labeled, then tran2 current through the terminal versus NV0, same sweep, then tran3 current versus the same sweep. So when you plot, you get the 3 sets of plots like this. Maximize it, then you will see. Now you see this red one is IV0. This is tran1 at RS is equal to 0.1 ohms. Now blue one, tran2, is for the case when RS is equal to 0.3. This is for the case when RS is equal to 0.6, and it is also agreeable with the theory that we had discussed earlier, and the RS non-ideality causes quite a lot of distortion as it increases. So quit this and you can exit out of the ngspice environment. Sometimes you may want to run the analysis repeatedly many times, and then every time for you to type within the ngspice environment may be cumbersome. So what you could do is, now let me go into the ngspice environment. Now let me type history. You know the history of commands that you have done previously. You can now go to pv.cir, open that, and let us put in the control scripts. So between control and .end-c, you can put in all the scripts that you had typed here and whatever is relevant to you. So let us say we wanted to first run the simulation with RS is equal to 0.1. Then we would like to alter RS to 0.3 and then run the script. Then again alter RS to 0.6 ohms and then run the script. Now we have 3 analysis, tran1, tran2 and tran3. We would like to set plot to tran1. Then we did a set color of the background to white, set color of the foreground to black, and then we plotted the graphs. So what did we plot? So what is there here, I could probably copy that and then paste it here. So this is the analysis that we wanted to do and plot. So this I will save it and then close it. So now when you call ngspice, it will execute all these control statements and then provide you with the final results. So let me exit out of it, Control L, now clean slate, call ngspice pv.cir. So it will go through the complete set and execute and give you all the 3 results. So this will help you to do repeated simulations with minor changes. So you could make the changes directly here in the control statements. This will save on iteration.